Okay, example 2. The base of a solid is the region enclosed by the graph x equals y squared, the x-axis, and the line x equals 4. Cross-sections perpendicular to the x-axis are squares. Find the volume of the solid. So by giving us this information, x equals y squared, the x-axis, and the line x equals 4, that's giving us the base of the solid. So we'll have that. So we're going to go ahead and sketch the base. All right, x equals y squared is your sideways parabola, and it's also bounded by the x-axis and the line x equals 4. So this is kind of a good one to show here. So here's your sideways parabola. It is bounded by the x-axis and x equals 4. X equals 4, of course, is the vertical line right here. This is x equals y squared. And cross sections perpendicular to the x-axis are squares. So the one part I left out was the fact that this is bounded by the x-axis, which means this plays a role. Well, the area that's bounded by this is one of two areas. It's either all of this, or it's all of the one down here. It doesn't really matter which one you use, but it's only one of them because it is bounded by the x-axis, which means you have to stop at the x-axis. It's one of the bounds. So we're going to consider the top part here as our area, although it could have been the bottom part. It doesn't really make any difference. But the top is easier to deal with typically because you're dealing with the positive function values. So we're going to deal with this area right here. So this is the base of our solid. Again, remember, this is basically like looking straight down at the table, and this is the bottom of whatever this figure looks like. What it tells us is that the cross sections perpendicular to this are squares. So really, what we've got is something that looks kind of like this. There's a square there, but then as we go down, because this is a big square here, as we start to go more back towards the origin, the squares are going to start to get smaller. And then the closer and closer we get to the origin, the smaller the squares are going to become, all the way down to the point where we get to here. So hopefully you can kind of see that if I were to kind of connect that, you would kind of see the shape of this thing that's going to make. It's going to kind of come down here like this. So all these pieces here are going to be squares. It's going to look kind of weird actually. And then it's going to circle around the back like that. And this right here is our base right here. This is exactly this figure right here. This bottom part down here and the blue on the bottom is the base. So I don't know exactly what this thing is going to look like. It's going to look like, I don't know. I don't even know what you would call that. But this is it. This is the solid figure. You don't have to be able to draw this part, but you definitely need to understand this is the base. Cross sections are popping off the page, kind of like this is the bottom, and they're going to be squares. The squares have different sizes as we go down. So in order for us to be able to integrate from here to here, because it is going to be perpendicular, here's your cross section, it is going to be perpendicular to x-axis, we need to know how to find the area of a square. Well, hopefully that's not going to be too difficult. You guys should all know the area of a square is side squared. The side squared. All right, typically I won't use s's because they look too much like 5s, but that's how you find the area of a square. And in this case, the side, or one side, is determined from the distance from here to here. That's this one right here. From the bottom up to the top of the function. From the x-axis, which is what this is, up to the function. So that's one side, and that side is determined by this function right here. Why this is solved for x already, I'm not sure, because really this is going to be perpendicular to the x-axis, so we need this solved for y. So really that's going to be y equals taking the square root of both sides. It's the plus or minus square root of x, but of course we're only talking about the top part, so it's really just the square root of x. So that is my side. So in this case, our side is the square root of x. And if I want to find the area, it's going to be the side squared. And I'm going to add all those up, so we're going to integrate. So we're going to integrate, looks like we're going from 0 to 4. So find the volume, integral, 0 to 4, of the side squared, which is root x squared dx. This one's going to be really simple. Notice that there is no pi in this. Okay, we have nothing to do with pi when we're taking the areas of squares. Has nothing to do with pi. That's one of the biggest things that people mess up on, is like, where do I put the pi? There's no pi in this. It's not, again, we're not revolving this, creating circles. We're not taking areas of semicircles or anything circular. This is the area of a square, and we're adding all those up. So x squared, of course, is just x. Antiderivative of that would be 1/2 x squared from 0 to 4. And that is going to be 16 over 2 is 8 minus 0. So we get a volume of 8, whatever the units are, cubed. All right, it would be really nice if they were all actually that easy algebraically, but they're not. All right, example 3. Base of a solid is the region enclosed by y equals 1/2 x squared and y equals 8. Cross sections perpendicular to the y-axis this time are semicircles with the diameter in the plane of the region. Find the volume. So again, we're going to try and sketch this thing because it does help. 1/2 x squared, that's just a parabola, a little bit wider opening than a normal one, but oh, that was nasty. Okay, a little better. And y equals 8, horizontal line here, and that's y equals 1/2 x squared. Let's see. Base of the solid region enclosed by that graph and that line. Cross sections perpendicular to the y-axis. Let's do perpendicular to the y-axis. Looks like that. Are semicircles with the diameter in the plane of the region. So this whole thing right here is the base. That's the diameter of the semicircle. Now you have to imagine that the semicircle is coming up off of the page. So let's see here. This is the diameter. That means this is the radius. And we know we need radius for a semicircle. Also, we're doing this thing perpendicular to the y-axis. That means I need to solve that equation right there for x. So let's go ahead and do that first. So solving that for x, let's see, we're going to multiply both sides by 2y. I mean by 2. So we'll get 2y equals x squared. Taking the square root, x is going to be the plus or minus root 2y. And again, we only need to consider one side, so we're going to consider the right side, the positive of that. That's the square root. No, let's not write it like that. We're going to say, oh, I think I'm actually ahead of myself. Let's go down here. The radius, yeah, here it is. So the radius of the semicircle is just the positive root 2y. All right, so we have our radius, because that's this green line right here. And now that we're going with respect to y, we're going to go from here, which is 0, up to 8. So the volume equals the integral 0 to 8. And the area of the semicircle is 1/2 pi r squared. Our r is root 2y. And because it's y, it's going to be dy. All right, so this one actually should work out pretty nicely as well. Let's take the 1/2 to the front. 1/2 pi. Squaring that gives us integral 0 to 8 of 2y dy. I can actually pull the 2 out to the front if I want. That's going to be 2 times 1/2. That's going to leave us with pi. Integral of y is 1/2 y squared from 0 to 8. Plugging in 8, 64 divided by 2 is 32. 32 pi. Plugging in 0 gives us 0. So the volume of this in particular figure is 32 pi. And that was if we had some kind of a base which was bounded by that parabola and the line y equals 8, and the cross sections were semicircles. So there you go. That should take care of it. That should be enough. The WebAssign will be available as of Friday morning, and the instructions will be on Classroom.